mathematics is the language in which God has written the universe. However, mathematics behind the workings of universe is so subtle that we need to delve a little deeper to comprehend the fundamental laws upon which the universe is built. Let's consider a cube which follows a simple rule. It grows in such a way that it doubles its current weight in the next day. So, if the weight of the cube at Monday 10 am is 1 kg, what will be the weight of the cube at Tuesday 10 am? 2 kg, right? Because it will grow in such a way that it doubles the weight. But the devil is in the details. It's not how much it grows, but how it grows. According to our assumption, the cube grows uniformly continuously at a rate of 1 kg per day. So, according to this, the weight of the cube when 1/10 of the day passes after Monday 10 am will be 1.1 kgs. So, now the cube will start to grow in such a way that it needs to double this weight in next 24 hours, which will lead to weight more than 2 kg at Tuesday 10 am. But wait, will the weight be 1.1 kgs when 1/10 of the day passes? When 1/100th of the day passes after Monday 10 am, according to our assumption, the weight of the cube would have been 1.01 kg. When the cube tries to double this weight in next 24 hours, it will start growing at a rate of 1.01 kg per day, which will lead to a weight more than 1.1 kg when 1/10 of the day passes. So, at what point the cube stops growing at the rate of 1 kg per day and updates itself to a higher growth rate? That's the catch. The very moment the cube starts growing, it changes into some other cube and starts growing more fastly. So, according to this, the weight of the cube by the end of one day should have been infinity. But no, the weight of the cube will not even cross 3 kgs. But how? Let's see in this video. Before seeing how, we'll see why we need to know about this kind of growth. What in the world grows like this? Well, everything in the world grows and vanishes following this rule. From growth of population to spreading of disease to a cup of coffee cooling, everything in the universe which grows and vanishes follows this rule. After John Napier discovered logarithms in 1618, William Oughtred, an English clergyman, compiled it and was writing an appendix of it. And he was having a curious question. He was facing this question when he tried to differentiate exponential functions. Exponential functions are those in which the variable is the power of a constant. Example, 2 power x, 3 power x, 4 power x, 1.5 power x, pi power x, all these are exponential functions. So when he was trying to differentiate 2 power x, which by conventional method we use the formula limit del x tends to 0 f of x plus del x minus f of x by del x. On substituting 2 power x in the place of f of x, we get limit del x tends to 0 2 power x plus del x minus 2 power x divided by del x. By taking 2 power x as common and outside limit, we get 2 power x into limit del x tends to 0 2 power del x minus 1 divided by del x. So on differentiating 2 power x, I get the same 2 power x multiplied by a limit. What's the value of that limit? When we try to plot the limit against del x, we get the value when del x tends to 0, the value of the limit tends to 0.6931. What's this value? we'll come to that later. When we do the same thing with 3 power x, we get 3 power x into 1.098. For 4 power x, we get 1.386. So clearly, as the base increases, the value of the constant also increases. The question William had was, somewhere between 2 and 3 there exists a constant which when raised to the power of x and differentiated gave the same function. So there exists a function whose rate of change at a given point is equal to the value of the function at the given point. So what does this have to do with our growing cube problem? If we look closely, the rate at which the cube grows will always be equal to the weight of the cube. When the weight of the cube was 1 kg, it grew at a rate of 1 kg per day. When it was 1.01 kg, it grew at a rate of 1.01 kg per day. So both William Ockert and us are looking for the same number, and he found out that the constant was an irrational number and the first few digits of that was 2.71828. He represented this constant as C, which in later years was named as Euler's number due to his contributions in this field, and was represented as E, and that's the origin story of the famous e power x, which is immune to both differentiation and integration. So what are those constants we got while differentiating the values other than e power x? If we look closely, we find these values are natural logarithms of the bases. Natural logarithm is the logarithm of base e, and that's how the clergyman working on John Napier's logarithmic appendix fell into this problem and accidentally discovers the Euler's number e. Let's try to systematically formulate a value of e. We know from the differentiation that limit del x tends to 0, e power del x minus 1 over del x is equal to 1. So for what value of e will this become true? We know as limit del x tends to 0, del x over del x is equal to 1. So if I somehow make the numerator del x, I will achieve the required result. So to make the numerator del x, I need to make c power del x minus 1 is equal to del x. So I am substituting del x in place of c. I get del x power del x. So to compensate for the del x in the power, I am substituting del x power 1 over del x. So now the del x in the power, it's getting compensated, but still I have a 1 outside. So inside I am also writing 1 plus del x. So 1 plus del x to the power of 1 by del x when del x tends to 0 is the value of e. If I substitute the value of del x to be 1 over n, then when del x tends to 0, n will tend to infinity. So the equation becomes e is equal to limit n tends to infinity 1 plus 1 over n to the power of n. If we observe closely, this is the equation of compound interest. So we can derive the value of e in terms of compound interest also, which is well explained in these videos which you can refer.